All right, so now we're going to talk about putting all that together. So we saw that P1 V1 equals P2 V2. That's Boyle's law. P1 over T1 is equal to P2 over T2. That's the Gay-Lussac law. V1 over T1 is equal to V2 over T2. That's Charles' law. And V1 over N1 is equal to V2 over N2. That's Avogadro's law. It's not, to me, it's not so important that you know the names of all these and how they're related to, which law it relates to, because we have the combined law, and that's really what I use when I kind of solve these problems. I don't worry about the individual laws. I always just use the combined law. And the combined law will help us derive any individual one that we want. Before we get into that of using it and showing you how it's used, let me just remind you about cross-multiplying, or show it to you if you have never seen it this. So we have some relationship where we say A over B is equal to C over D. And what cross-multiplying will do is allows us to quickly do the algebra to isolate any variable. And that's what we're going to do a lot of in this section. And the idea is, how do you get, say, D, which is in the denominator, how do we isolate it? How are we going to get it all by itself? And the idea of cross-multiplying is if you take one variable and move it to the other side, it goes to the opposite side, but also into the opposite part of the fraction. So things that start off in the denominator, when they move over, they end up in the numerator. And things that start off in the numerator, when they move to the other side, they go to the denominator. So that's how I think about moving and rearranging variables, and we'll have to do a lot of that. Sometimes this could be useful as well. You can take inverses. So A over B is equal to C over D. So you're allowed to invert the entire equation, and you can say that B over A is equal to D over C. So that's still true. And then once you have it rewritten this way, maybe you want to isolate B. So then you move A to the other side. So then it would be D times A over C. So this is how you should do your algebra. It works, it's very quick, and you're less likely to make errors. So how do we use the combined gas law? So in this example, say we're given pressure 1 and pressure 2 and T1, and we're asked to find the final temperature. It could be something like, the initial pressure was 1 atmosphere and the final pressure was 0.5 atmospheres when the temperature decreased the initial temperature was 50 degrees Celsius. What's the final temperature? So what that implies is that we're not changing the volume and we're not changing the moles. So anything that's constant in the problem, it'll either specifically tell you the variables are constant, or it just won't talk about them, which in that case, you can assume they're constant. So you just remove them from your equation, and that leaves you with P1 over T1 over equals P2 over T2, which is the Gay-Lussac law. You don't have to memorize that it was P1 over T1 equals P2 over T2. It just works itself out. And then you plug in and solve. In this case, we're going to use cross-multiplying to try to solve for T2. So I can quickly cross-multiply. So my T2 is going to go to the top. If I'm isolating the variable, I do want to have it in the numerator. And so that would leave me with T2 times P1 over T1. Now I just want to get rid of the P1, so I'm going to move it back down. So basically, P1 is going one way, and then T2 is going the opposite way. And then T1 will go up here. And so when I'm done, I'm left with T2 is equal to P2 times T1 over P1. Then you just plug in the variables, and it gives you an answer. Things to remember, it doesn't actually matter what units P2 and P1 are in as long as they're the same. So they could both be in atmospheres, but they both could be in pounds per square inch. It really wouldn't matter. You would get the right answer. T1, on the other hand, it must be in a specific unit. It must be always in Kelvin. And again, the same idea could work with 3 variables. So in this case, we're given 3 variables, P1, P2, T1, T2, and V1. and they ask us to find V2. Once again, they could specifically tell us moles are constant, or they could just never talk about moles, in which case we'll assume that moles are constant. So if moles are constant, cancel those out, and we'll be left with this expression. This isn't a named law, but this is what we need to know. And then using cross multiplying, we can solve for V2. So we send T2 up, we send P2 down, and we're left with P1 V1 T2 is equal to T1 P2, or over T1 P2, and that's equal to V2. And once again, we plug in and we solve. P1 and P2, once again, can be in any units as long as they're the same. T2 and T1 must be in Kelvin. If you don't do it in Celsius or Fahrenheit or any other unit, you'll get a number, but it's not going to be correct. V1, this can be in any unit as well. So if this was in milliliters, it'll still work, but your V2 will be in milliliters. If your V1 is in liters, your V2 will be in liters. So whatever unit you have here, you'll get the same unit out as V2. But if you want to be consistent, you can always just make sure you're always plugging in liters. There's also the universal gas constant, R. So the reason why we can do this with the combined gas law is that P1, V1, N1 over T1 is always equal to the same number. And that number is R, the universal gas constant. So this set, for any set of pressure, volume, moles, and temperature, it always must equal to R. And what is the value of R? It depends on what units you're using, but if you're using liters, atmospheres, moles, and Kelvin, the value of R will be 0.0821. And if you're using kilopascals, liters, moles, and Kelvin, your value would be 8.314. So just pay attention to which value of pressure you're using, and then you can use this idea of R. Usually it's rewritten, and it's written as PV equals nRT. And it's a very useful equation, because if you know three variables, then you can always figure out what the fourth variable is. So if you knew what the pressure, volume, and temperature was, then you can figure out how many moles of gas there are. If you know the volume, moles, and temperature, you should be able to figure out the pressure. And the only thing, you just make sure that you're using the correct R value, and it'll give you what units your pressure's in. We did this problem where we solved for the V2 when given three variables. We could also solve this not using combined gas law, but the ideal gas law. And the solution is pretty similar. So here's the setup of the problem. This is exactly like I described previously, but our solution will be a little bit different. So what we're going to do is we're just going to use all the ones that are labeled by 1, and we're going to solve for our unknown. So we're told what P1, V1, and T1 is. We already know what R is. We can figure out what N1 is. So we find the value of N1, and the idea is, in the problem, N1 was a constant. So N1, the moles in the first setup, is the same as N2, the moles in the second setup. We didn't alter the amount of moles in the system. So now you know what P2 is told to you in the problem. You know what T2 is told to you in the problem. We've already solved what N2 was, so we know this, 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 and this, and now we can go back and solve for V2. So both methods will work, and both methods will give you basically the same answer for V2. I have no real preference. I've noticed that mostly students like to do it this way, and that's fine, but do try using the combined gas law to solve for these things as well.